Okay, thanks for coming to my e-poster. I'm Alex Becker, and today I'm going to talk about long-term dynamics of measles in London, titrating the impact of wars, the 1918 pandemic, and vaccination. This was a collaboration with Amy Weslowski, Attar, and my advisor at Princeton, Brian. So just give some background quickly. A key question in nonlinear dynamics is how perturbations to a system impact long-term trajectories. So if you change contact rates, add, remove people, increase birth rates, how does the system respond and what do dynamics look like? Measles has been analyzed extensively for this question for two main reasons. One, there's a lot of data available in a variety of settings, so US, UK, and Niger. And also has relatively simple models and life history. So once you get measles, you have immunity for the rest of your life. So briefly, the goals of this analysis were to extend the data by 50 years and analyze four key perturbations. So the World War I, demographic changes, changes in contact associated with the 1918 pandemic, demographic changes in World War II, and the start of vaccination in 1968. So briefly to do this, we collected 100 years of data ranging from 1897 to 1991. So these are mortality counts and case counts. And we fit the whole time series in tandem using maximum likelihood methods to switch between mortality and morbidity. And we estimated essentially 10 parameters: initial conditions, time-varying seasonality, and a reduction in contact due to the 1918 pandemic. And we assessed the fit visually and via tractor analysis, which we'll talk about now. So just to zoom in on these figures. So figure one briefly will show the data. So the main take homes here are births and populations basically mirror each other. You have these dips associated with the world wars, and then these increases in births and population in both. And vaccination starts in 1968 before ramping up. And these are mirrored in the demographics. So the first half is death data, second half is case data. And the main take home here is that these patterns switch from annual, like in 1905-ish, to biennial, like in 1920, 1950. So we fit this model and we simulated it to compare against the data. So the data here is now shown split by deaths and cases in red, inverted, and the model is shown in light blue. In general, visually, we capture the dynamics pretty well, especially simulating 100 years ahead. And this is all from one seasonality. So you see these high points here, these correspond to when school is in session, and these low points, school holidays, so summer and Easter. And the main thing here is visually we're matching the dynamics. When it's biennial here, it's biennial here. Same with 1950. But we can look at that with more rigor via power spectra. So if we take the dynamics here and we color code them by periodicity, so are you annual or biennial, we can simulate the model 10,000 times, do the same thing for each simulation. So to start, in early 1900s, data was primarily annual, the model is generally annual. But you have this quick bifurcation from annual to biennial in 1920. This is actually the 1918 pandemic. We estimated a 40% reduction in contact due to closures, et cetera, things that we're seeing now. And the model remained biennial, both in data and the simulations, until 1950, when it went from annual to biennial again. This is from the World War. And if we look at global power spectra, we generally see strong agreement with peaks at 1 and 2 years. But one thing we notice if we zoom in is that in the World War II era, we didn't really have a great match between data and model. So this is a top panel, just zoomed in from what you've seen in figure 2. But if we just fit the 6-year chunk for World War II, we actually see a much better fit to the data. And as a consequence, we see much flatter seasonality. You still have these peaks related to school term, but they're much flatter. And if we do this 6-year kind of epoch analysis across the whole time series, this is the flattest seasonality across the whole bit. So just that now that my time is kind of running out, we have major conclusions so that the model gives a strong agreement to the data via visual fit, periodicity, and R naught. We found a 40% reduction in contact due to the 1918 pandemic. The World War II region shows less of a signal of school term forcing, likely due to the World War II evacuation, which brought 1 million children out of London into the countryside. And this is generally just another example of how simple models can capture an array of complicated dynamics spanning 100 years, which is just a very cool result for dynamical systems. So if you have any questions or comments, please feel free to email me at adbecker@princeton.edu. And thank you for your time.